Today, Ruoyang and I will be introducing the discoveries of William and Lipscomb, which is the determination of boron structures specifically by using X-ray crystallography and NMR techniques. So firstly, some background information. William Lipscomb was an American chemist who, in 1976, was awarded the Nobel Prize in Chemistry for his studies on the structure of boranes, which are boron-hydrogen compounds. Lipscomb combined experimental and theoretical methods to show how electron-deficient atoms can form stable compounds. His study inspires the investigation of many other cluster compounds, which now sees applications in materials and catalysis. There were two critical physical methods behind Lipscomb's discovery. The first was X-ray crystallography, which yields precise atomic positions and complex geometries, allowing the inference of bonding patterns. The second was NMR, specifically boron-11 NMR, which, by visualizing the different chemical environments, greatly accelerated boron structure determination. To understand the importance of physical methods toward Lipscomb's discovery, we must first learn a bit more about the theory of boron structure. The theory of boron structure started with the exploration of this compound, diboron, where two of the hydrogen atoms are bridging between the two boron centers, forming three centers, two electron bonds. This bonding paradigm was applied by Lipscomb toward boron clusters, where he described the bonding between three boron atoms using either the three-center central or the three-center open models. Then, these models are used toward understanding the structure of boron clusters, such as pentaborane shown here. Lipscomb constructed symmetry-adapted linear combinations and formed these hypotheses. In these diagrams, we can see that the hydrogen atoms take the form of either bridging or terminal hydrogen atoms, and that the boron atoms can be in either a BH unit or a BH2 unit.
I want to first start with the X-ray crystallography introduction. X-ray diffraction is a powerful technique that was used to determine the atomic and molecular structure of crystalline materials. When crystal is exposed to X-ray, the beams are diffracted in specific directions based on the crystal's internal lattice. By measuring the angles and intensities of these diffracted beams, a 3D electron density map can be constructed, which reveals the position of atoms with crystal. XRD is essential in chemistry, material science, and biology for identifying unknown compounds, analyzing the crystal purity, and solving complex molecular structures, which includes the inorganic clusters like boron that are studied by William Lipscomb. So shown here in the plot is a very basic and abstract setup for the X-ray diffraction. We have a holder that can hold the high-quality single crystal needed for the X-ray diffraction, and we have beams that project through this single crystal sample. It can be rotated so that the diffraction pattern can be collected. And after we got all the diffraction pattern, we will do the data processing and refinement to build up the electron density map and help us find out the actual atomic structures right there. I want to use the example of B9H15 to help demonstrate how X-ray crystallography can be helpful in determining the atomic position and structure in boron. So in X-ray diffraction, the very straightforward data we get is the diffraction pattern. We think that there are Miller indices, HKL, which describe the orientation of crystal planes that causes the diffraction. It also provides data about the diffraction intensities, and with intensity we can calculate for the amplitude by simply taking the square root. We get the absolute value of the structure factor amplitude. With all these data, we can start solve for the phase angle, which prepared us for the Fourier synthesis. By plugging the variables right here, we can find the electron density maps. So the Fourier synthesis is a mathematical tool that we use to help combine the structure factors and compute the electron density map. This electron density map will help us to reveal the atomic positions within the unit cell, and the process enables precise determination of molecular and crystal structures. So here I actually want to talk more about the Fourier synthesis, which is a mathematical tool that we use to build up the electron density map, as I mentioned in the previous slides. So you may notice here on the row x, y, z, this variable represents the electron density at any point in the unit cell, and the V is the volume of the cell unit, And the F here introduces the structural factor, which is a complex number containing the amplitude and phase angle. The exponential term introduces the phase shifts that vary with position, and by summing all these waves' contributions, the electron density distribution is constructed in the real space. This allows chemists to visualize atomic positions and bonding in a crystal. Shown in the plot right here is actually the structure and the electronic density map built up by the Lipscomb in his paper back to 1957. Generally, with the Fourier synthesis, we are able to get the electronic density distribution over the real space, and this helped us to visualize how the crystal structure could look like. With the known electronic map and deduced boron skeleton, it is possible to do some refinement to better locate the accurate position of boron atoms. Lipscomb used the least square method as a mathematical refinement tool to improve the proposed crystal structure by minimizing the difference between observed and calculated diffraction data. Specifically, it adjusts atomic positions and thermal parameters to minimize the residue. As you can see here, two equations have been proposed representing two different approaches. In the first equation, there is a weight coefficients for different reflections, the strong and weak ones. Intensities do matter here. And in the second equation, the weight coefficient disappears. And Lipscomb has proposed that the weight coefficients of strong and weak refractions could help finding out the difference in the residue more precisely. Since the strong reflection naturally has low relative uncertainty, so they should have a lower weight to prevent them from dominating the refinement. And weak reflection has higher relative uncertainty and are prone to noise, but they contain critical information about minor electron density and bondings. As a result, the different weight coefficients should be applied when we are doing refinement.
After obtaining the boron skeleton, now it is time for placing the hydrogen atoms and figuring out the complete structure, which is also the most important part of Lipscomb's work. The configuration of hydrogen atoms is confirmed with the computation of the difference between the observed and calculated Fourier map. These maps revealed peaks corresponding to the missing atoms, and here is the hydrogen atoms. It also includes those bridging positions which form the three center 2 electron bonds. By overlaying these residue peaks onto the known boron skeleton, Lipscomb could assign hydrogen positions with high confidence, and the plausibility of this placement was confirmed through the bond length analysis and the refinement analysis. So as you can see in the equation here, the delta rho represents the change of electronic density in two different maps, and it indicates the possible position of the hydrogen atoms. So in the plot here, two different models were proposed. Model A and Model B are actually only geometrically different in the position of HM and HO, these two hydrogen atoms. Lipscomb used these two ways to approach the validation. The first is the bond length analysis. In the correct model, the boron-boron distance ranged from 1.7 to 1.85, which are consistent with the typical boron-boron single bond, and boron-hydrogen bridging bonds are around 1.25, which aligns with the known 3C2E bond values. In addition to that, he also did a refinement to these two models, and he found out that HM and HO moved 0.55 in Model B, and in Model A they only moved 0.25. And overall, the final agreement factor R for all the planes that could be obtained in the molecule are still lower for the Model A than Model B. So he reached the conclusion that Model A is the actual structure of the B9H15.
So aside from crystallography, the other important physical method to this discovery is NMR methods. So in NMR, researchers place samples most commonly in solution under a magnetic field and measure the excitation frequency of NMR active nuclei, which is altered by the chemical environment and reflected in the chemical shift. Lipscomb recognized the importance of NMR to structure determination and came up with empirical and theoretical approaches for using NMR. In the empirical approach, researchers observed the chemical shifts of boron in different boron clusters, while in the theoretical approach, computational chemistry was applied to predict NMR chemical shifts. There are two common nuclei used for the NMR analysis of boranes. The first one is boron 11, which is a quadrupolar nuclei of 80% abundance. Despite being quadrupolar, it does show sharp peaks for tetravalent boron centers. and it has a large range of chemical shifts which facilitates analysis. Furthermore, the splitting pattern of boron 11 is particularly valuable as it can directly tell us whether each boron atom in a borane is in a BH unit or a BH2 unit. Subsequently, the other type of nucleus used is the proton, which has been 1/2 and is very highly abundant. It also has a high gyromagnetic ratio of roughly 3 times of that of boron 11, leading to a higher sensitivity. However, it does have a small range of chemical shifts, and especially in older instruments with a weaker magnet, it can make the peaks hard to resolve. The first example of boron structure determination by NMR that we will examine is hexaboron 10. Based on crystallographic evidence, it was proposed that hexaboron 10 had this pentagonal pyramidal structure, with 1 apical boron atom and 5 basal boron atoms. Each of the boron atoms is part of a BH subunit. The 4 remaining hydrogen atoms act as bridging hydrogens along the base. So, the NMR evidence shows us that there are 2 chemical environments in this species, both of which are doublets, which easily confirms the fact that all of the boron in this atom are in BH units. Furthermore, however, since this species has 4 bridging hydrogen atoms only, we would expect 4 distinct boron chemical environments, yet we only observe 2, of which all of the basal boron atoms are in the same chemical environment. Hence, this leads to a hypothesis that there was rapid proton exchange occurring within this compound. A logical method to explore this proton exchange hypothesis is with proton NMR. However, the initial spectrum collected on a 40 MHz instrument was quite poorly resolved. This resolution was improved using a 100 MHz instrument in which at -80 degrees Celsius we only see 2 peaks, but more peaks appeared when we use -150 degrees Celsius for measurement. So these different peaks are assigned to different hydrogen atoms on our compound. Subsequently, we can see that for the upfield chemical shift peak that correspond to the terminal hydrogen atoms on the basal boron atoms is split into 3 different peaks at a lower temperature corresponding to 3 different chemical environments of the basal boron atoms. Furthermore, the more downfield peak split into 2 peaks representing the 2 chemical environment for the bridging hydrogens and also revealing a hidden peak for the terminal hydrogen atom on the apical boron atom. A different example of boron structure determination with NMR is hexaboron 12. In its NMR spectrum, shown here, we can see that there are 3 distinct chemical environments, a doublet, a triplet, and another doublet that overlaps with a triplet. This indicates that hexaboron 12 has 2 distinct boron chemical environments with BH units, as well as 2 boron atoms with BH2 units. And hence this supports Lipscomb's hypothesis for the structure of this compound, which looks like this. In the structure, B1 and B4 are the BH2 units, while the other 4 boron atoms form the 2 distinct BH units. Modern advances in NMR instrumentation allows for better boron structure determination. Shown here is an example in which a stronger magnet, roughly 10 times the strength of the magnets we've previously seen, is used to determine boron structure. In this case, the splitting pattern of the boron NMR is really well resolved, and it allows us to determine the structure of complex borons like the structure shown on the left. Stronger magnets also enables the use of 2D NMR techniques. Shown on the left is an example of boron 11 cozy, in which the correlation between neighboring boron atoms and boron molecules can be investigated. Shown on the right is an example of proton boron 11 HMQC, which explores the correlation between boron atoms as well as the terminal and bridging hydrogen atoms connected to it. In conclusion, physical methods shown here supports the development of Lipscomb's bonding theory and justify the electronic structures he proposed. Specifically, NMR studies complement crystallographic evidence by filling in the missing gaps, such as the difficulties in determining the locations of hydrogen atoms. Moreover, this shows that heteronuclear NMR and splitting patterns in NMR are crucial tools to understanding bonding in inorganic chemistry. Furthermore, more powerful instruments such as stronger magnets can facilitate structural determination. Thank you.